Hello friends. So in this video we're going to be discussing dimensional analysis. How true. So what is dimensional analysis? Dimensional analysis is an expression which shows how fundamental quantities such as mass, length and time are represented by the letters M, L and T respectively. Dimensional analysis is an expression which shows how fundamental quantities such as mass, length, and time are represented by the letters M, L, and T respectively. Now, what then would be the application of these dimensional analysis? The applications of dimensional analysis would include 1. To establish formulas. How true dimensional analysis helps us to establish formulas. The second would be to check the validity of an equation. Dimensional analysis helps us to check the validity of an equation. Another very important application to the dimensional analysis would be that it helps us to determine the unit of some physical quantities. How true? It helps us to determine the unit of some physical quantities. The fourth now would be that dimensional analysis helps us to determine the relationship between physical quantities. I repeat, dimensional analysis helps us to determine the relationship between physical quantities. How true? Dimensional analysis helps us to determine the relationship between physical quantities. Now, we say that our mass is denoted by M. Mass denoted by M. Our distance, which is also our length now, length is denoted by L, and our time is denoted by what? T. So let's find the dimension of certain physical quantities. For example, velocity. What would be the dimension for velocity? It is important to note that in understanding the dimension of these quantities, we must apply the formula. So, what then is the formula for velocity? The formula for velocity is given as distance over time. This is the formula. So, we know that the dimension for distance is L, the dimension for time is T. So, this gives us that the dimension for velocity is L T raised to power negative 1. So moving this t at the denominator upward, we have to give it a power of negative 1. This would be the dimension for velocity. Now, acceleration. How can we find the dimension for acceleration? Now, acceleration, you know that the formula is velocity over time. That would be the formula for acceleration. So therefore, we have that since we know that our dimension for velocity is Lt raised to power negative 1, and also our dimension for time is t, so we can solve our dimension for acceleration from here. So here, this gives us L, now t. Notice now that this could be resolved using the knowledge of indices. So we pick one of the t's at the denominator and numerator now, and we subtract the powers. So this gives us minus 1. And in the aftermath, we have that our dimension for acceleration is L t raised to power minus 1 gives us minus 2. This would be the dimension for acceleration. Now, let's try finding the dimension for force. Let's move the page upward a bit. Yes. Now, force. We know that the formula for force is mass times what? Acceleration. Mass times acceleration. and the dimension for mass is m. Dimension for mass is m. And from our findings now, we found that the dimension for acceleration was given as Lt raised to power minus 2. So we have mass times Lt raised to power minus 2. And in the aftermath, the dimension for force is given as mLt raised to power minus 2. This would be the dimension for force. Now, let's try finding the dimension for work done. Work done. We know that the formula for work done is force times distance, because work is said to be done when an applied force is moved through a distance. So that will be force times distance. Force times distance. And we know that the dimension for force we got to be mLt raised to power minus 2, and the dimension for distance is given as the same dimension for length, because distance is just a change in length. So our dimension would be L. So now, in the aftermath, we have that the dimension for work done would be m. Now, L times L give us L squared. Then T raised to power minus 2. So our dimension for work done is mL squared T raised to power minus 2. This would be the dimension for work done. Now, it's very important to note now that some of these quantities have similar dimensions. For example, work done would be equal to what? Energy. Yes, energy is equal to work done, and as such, they have the same dimension. Let's prove this a bit. So now, one of the formulas you know for energy now, for the potential energy is given. Potential energy PE is given as mgh. Now, m there would be mass, g would be acceleration due to gravity, and h would be what? Height. Now, the dimension for mass is given as m. Now, g is acceleration. G is equal to acceleration due to gravity, acceleration due to what? Gravity. So it is still acceleration, right? G is still acceleration. So the dimension for G would be the same dimension we got for acceleration. And recall now that the dimension we got for acceleration was, let me put a multiplication sign here, was Lt raised to power minus 2. This was the dimension we got for acceleration. Now, h here is height, and height would simply be a distance upward, right, or downward. So this would be, since height is also distance, so the dimension for height would be length. So we have times length. Now, our dimension for potential energy finally gives us m L. Now we have L here, we also have L after the multiplication sign. So we have L times L, which gives us L squared. So mL squared T raised to power minus 2. T raised to power minus 2. So this is the dimension for potential energy. Notice now that it's the same dimension we got for potential energy here that we also got for work done. So some of these physical quantities now, some of these quantities have similar dimensions. Let's try out one more. Now, power. What would be the dimension for power? Notice now that power is energy consumed in a particular time, right? So energy over time. That would be the formula for power. So, and we know that the dimension for energy is mL squared T raised to power minus 2 divided by time, which has the dimension t. Now, in solving this, we are going to have ml square t raised to power. Now, we pick one of the t's according to the laws of indices and we subtract the powers, right? So minus 2 minus 1. So the dimension for power gives us ml square t raised to power minus 3. There you have it, guys. This would be the dimension for power. There are so many other physical quantities we can find the dimension for. So we'll be doing that in the next video. Thank you so much for watching. See you in the next video.